Welcome to Dan. Don't forget to subscribe. The date is April 26, 1986. The time is exactly 1:23:40 a.m. In the deep, silent woods of northern Ukraine, just a few miles from the border with Belarus, the world is about to witness the impossible. Inside the control room of the Chernobyl nuclear power plant's reactor number 4, the air is thick with tension, not because of an impending disaster, but because of a routine safety test. The engineers in the room believe they are masters of the atom. They believe they are operating a machine so stable, so fundamentally safe, that it could be built in the middle of a crowded city without risk. But in the next few seconds, the laws of physics will turn against them. A low-frequency rumble, like the sound of a distant freight train, begins to shake the floor. Then a series of sharp metallic cracks, the sound of 350-kilogram fuel assembly caps jumping in their sockets like popcorn on a stove. Suddenly, the world explodes. A 2,000-ton concrete biological shield, a slab of material as heavy as 3 fully loaded Boeing 747 aircraft, is tossed into the air like a discarded coin. A pillar of blue and violet light, ionized air glowing with the sheer intensity of radiation, pierces the night sky, reaching heights that pilots would report seeing from miles away. This was the birth of a catastrophe that would redefine human history. But the most shocking revelation isn't the explosion itself. It's the fact that the very button meant to stop the reactor, the emergency shutdown switch, was the very thing that triggered the final, fatal surge. We are going to dive into the blueprints and the buried secrets to understand how the pride of Soviet engineering became a radioactive tomb. To understand why Chernobyl fell, we first have to look at the sheer gargantuan scale of the object itself. The RBMK-1000 was not just a power plant, it was a titanic achievement of human ambition. RBMK stands for Reactor Большой мощности канальный, which translates to high-power channel-type reactor. This wasn't a compact pressurized water reactor like those found in the West. It was a sprawling graphite-moderated giant. The core was a cylinder of graphite blocks 12 meters in diameter and 7 meters high. To put that into perspective, you can visualize, imagine a circular room the size of a professional basketball court, stacked nearly 3 stories high with solid blocks of pure carbon. Inside this massive graphite nest were 1,661 individual fuel channels, each one a high-pressure pipe filled with uranium-235 fuel rods. The total thermal power output of this single unit was 3,200 megawatts. That is enough raw energy to power 2 million modern homes simultaneously, or to light up the entire city of Chicago twice over. The reactor building itself loomed over the Pripyat skyline, a fortress of reinforced concrete standing over 70 meters tall, roughly the height of a 22-story skyscraper. It was a monument to progress, a concrete cathedral dedicated to the promise of peaceful atoms. Every number associated with Reactor 4 is mind-boggling. The cooling system required thousands of tons of water every single hour, circulating through miles of specialized zirconium alloy piping. The biological shield, nicknamed Elena by the workers, was a massive steel and concrete lid designed to keep radiation contained and allow workers to walk safely across the top of the reactor. This lid weighed 2,000 metric tons. Think about that weight for a moment. That is equivalent to the weight of about 1,300 mid-sized cars, all concentrated into a single circular plate. The fact that the internal pressure of the explosion was great enough to flip this plate onto its side is a testament to the unimaginable forces at play. This was a structure built to survive the impact of a falling airplane or a direct hit from conventional artillery, yet it was torn apart from the inside by a runaway physical reaction that lasted only seconds. The scale was so vast that when the explosion occurred, it didn't just destroy the room, it blew the entire roof of the 20-story building, scattering pieces of highly radioactive graphite across the grounds like deadly hail. What makes the story of Reactor 4 truly haunting is that it wasn't some experimental fringe project, it was the gold standard of the Soviet energy sector. It had been inspected by the highest levels of the Ministry of Energy and Electrification. It was certified as safe, reliable and efficient. In fact, the Soviet nuclear establishment was so confident in the RBMK design that prominent scientists famously claimed a nuclear accident was virtually impossible. They suggested that the RBMK was so stable you could build one in the middle of Red Square in Moscow and it would be as safe as a samovar boiling tea for a family dinner. It was a legal, regulated and heavily monitored facility operated by some of the most highly trained nuclear physicists in the world. There were protocols for everything, from the pressure in the steam drums to the exact percentage of control rods that had to be inserted at any given time. On paper, Chernobyl was a fortress of safety, and yet, on that April night, every single one of those assumptions was shattered. The inspectors had missed the flaws, the operators had misunderstood the risks, and the system itself had hidden the truth. As we peel back the layers of this catastrophe, we will see that the tragedy was not just a failure of parts, but a failure of a philosophy that believed human engineering could fully conquer the laws of nature. The disaster was already written into the blueprints long before the first shovel hit the dirt in 1970. To understand why the Chernobyl disaster was inevitable, we have to look past the concrete and steel and into the invisible world of nuclear physics and Soviet bureaucratic pressure. The catastrophe didn't begin on the night of the explosion, it began years earlier on the drawing boards of the Soviet scientific institutes. The RBMK-1000 was designed with a fatal flaw known as a positive void coefficient. In most Western reactors, water acts as both a coolant and a moderator that slows down neutrons to sustain the reaction. If the water boils away or turns to steam, the reaction slows down because there is no moderator left. It's a self-limiting safety feature, like a car that naturally slows down if you take your foot off the gas. But the RBMK was different. It used solid graphite as the moderator. In this design, water was primarily a coolant that also happened to absorb neutrons. If the water turned to steam, creating voids, there was less water to absorb neutrons, but the graphite was still there to keep the reaction going. This meant that as the water boiled, the reactor power actually increased, which created more steam, which increased the power even further. It was a terrifying feedback loop, an engine that would accelerate the hotter it got. The stage for the disaster was set by a botched safety test that had been postponed for years. The goal was to see if the spinning momentum of the turbine generators could provide enough electricity to run the cooling pumps during a power failure for the 40 to 60 seconds it took for the emergency diesel generators to start. It was a noble goal, a search for a higher safety factor, but the execution was a masterclass in human error. On April 25th, the reactor was scheduled to be powered down for the test. However, the local power grid controller in Kiev demanded the plant keep producing electricity to meet unexpected industrial demand. For 9 hours, the reactor sat at half power. During this time, a poison began to build up inside the core, xenon-135. Xenon is a byproduct of nuclear fission that loves to eat neutrons. At full power, it is burned away as fast as it is created, but at low power, it accumulates, acting like a giant wet blanket over the nuclear fire. Think of it like trying to start a campfire with logs that are soaking wet. The xenon was smothering the neutron flux, the invisible wind of particles that keeps the reactor alive. By the time the night shift took over at midnight, the reactor was dangerously unstable. When they finally got permission to drop the power further for the test, the power plummeted almost to zero because of the xenon poisoning. The lead engineer, Anatoly Dyatlov, under immense pressure to complete the test before the scheduled maintenance shutdown, ordered the operators to bring the power back up. To do this, they had to pull the control rods out of the core. These rods are the brakes of a nuclear reactor. They are made of boron carbide, which absorbs neutrons and stops the reaction. The safety protocol stated that at least 15 to 30 equivalent control rods must remain in the core at all times to maintain the operational reactivity margin, or ORM. This is essentially the reactor's load capacity for safety. If you pull too many rods, you lose the ability to shut the reactor down quickly. On that night, the operators pulled nearly all of them. Out of 211 control rods, only a handful remained deep enough to be effective. The reactor was now like a massive 2,000-ton steam boiler with the safety valves welded shut and the brakes removed. The final, fatal mistake involved the very design of those control rods. In a cruel twist of engineering irony, the rods were tipped with graphite. While the boron middle section of the rod was meant to stop the reaction, the graphite tip actually displaced water and increased the reaction. It was like a brake pedal that, for the first few inches of travel, actually acted as a fuel injector. As the test began at 1:23:04 a.m., the cooling pumps were slowed down, reducing the flow of water. Within seconds, the thermal power began to rise. The water in the channels began to boil rapidly, triggering that positive void coefficient we discussed. More steam meant more power, which meant more steam. The reactor was entering a prompt critical state, a runaway chain reaction where the power increases exponentially in milliseconds. The operators saw the warning signs on their displays, but the angle of inclination of the power curve was now vertical. At 1:23:40 a.m., an operator pressed the AZ5 button, the emergency scram that drops all control rods into the core at once. But it was too late. As those 211 rods moved down, the graphite tips entered the core first, causing a massive, localized surge in power at the bottom of the reactor. The fuel rods began to shatter under the yield strength of the internal pressure, the channels deformed, and the control rods became stuck, unable to go any deeper. The point of no return had been crossed. The reactor wasn't just melting, it was turning into a massive, pressurized steam bomb. At 1:23:45 a.m., the silence of the Ukrainian night was shattered by a sound that witnesses described as a low-frequency groan, followed by a thunderclap that seemed to come from the bowels of the earth. The second explosion was so powerful it registered on seismographs as far away as Scotland. Inside the reactor hull, the unthinkable had happened. The internal steam pressure had spiked to over 500 atmospheres in less than 3 seconds. To visualize that, imagine the weight of 5 Burj Khalifas, the world's tallest building, pressing down on every single square inch of the reactor's internal surface. The zirconium alloy pipes, built to withstand incredible yield strength, simply disintegrated. The 2,000-ton upper biological shield, which had sat firmly for years, was blasted through the roof of the building. It flipped in mid-air and landed back down at an angle, exposing the burning, incandescent core of the reactor to the open atmosphere. In those first few seconds, a pillar of blue light shot into the sky. This wasn't a Hollywood effect, it was the physical manifestation of ionized air and Cherenkov radiation. It was beautiful, ethereal, and utterly lethal. The radiation levels on the roof of the turbine hall were now upwards of 15,000 rengens per hour. In this environment, a human being receives a fatal dose of radiation in less than 60 seconds. That is about 200,000 times the dose of a standard chest X-ray, concentrated into a single minute of exposure. The onboard computer records from the Scala system, the plant's central monitoring brain, froze at the moment of the blast, leaving behind a digital ghost of the reactor's final parameters. The human stories that emerge from the rubble are as harrowing as they are heroic. Valery Perevodchenko, the reactor section foreman, was one of the first to look into the open core. He saw a shimmering, glowing mass where the reactor used to be and knew instantly that everyone in the room was already dead, himself included. Despite this, he ran through the radioactive steam to find his subordinates. Then there were the firefighters, led by 23-year-old Lieutenant Vladimir Pravik. They arrived within minutes, wearing nothing but standard canvas uniforms and helmets. They had no idea they were fighting a nuclear fire. They believed they were just putting out a blaze on the roof of the turbine hall. They handled chunks of burning graphite with their bare hands, graphite that was so radioactive it felt like it was biting their skin. All of the first responding firefighters would succumb to acute radiation syndrome within weeks, their bodies literally breaking down at the cellular level. The city of Pripyat, a model city of 50,000 people located just 3 kilometers away, slept through the initial blast. It wasn't until 36 hours later that the evacuation began. The announcement was chillingly calm, telling residents to take only what was necessary for a 3-day trip. They left their pets, their family photos, and their warm meals on the tables, never to return. The Bridge of Death, a railway overpass with a clear view of the plant, became a local legend where people supposedly gathered to watch the beautiful rainbow-colored fire, unaware that the wind was bathing them in a concentrated plume of radioactive dust. While the total number of immediate deaths was officially recorded as 31, the long-term impact involves thousands of liquidators, the 600,000 soldiers, miners and volunteers who were called in to clean up the mess. The investigation that followed was a battle of narratives. The Soviet authorities initially blamed the disaster entirely on operator error, claiming that the staff had violated every protocol in the book. During the 1987 trial in the city of Chernobyl, the plant director Viktor Bryukhanov, chief engineer Nikolai Fomin, and deputy chief engineer Anatoly Dyatlov were all sentenced to 10 years in labor camps. They were accused of criminal negligence and failing to follow safety standards. However, the data logs eventually revealed a deeper truth. Valery Legasov, the lead scientist investigating the crash, risked his life and career to reveal at a Vienna conference that the reactor itself had a fundamental design flaw. The critical decisions weren't just made in the control room that night. They were made years earlier by bureaucrats who prioritized cost-cutting and speed over safety. The punishments handed out to the operators were only a half-truth, masking a systemic failure that the Soviet Union was desperate to hide from the rest of the world. The legacy of Chernobyl is not written in the ruins of the power plant, but in the radical transformation of global nuclear engineering. For decades, the Soviet Union had operated in a vacuum of secrecy, but the radioactive clouds that drifted over Europe forced a level of transparency that had never existed before. The immediate engineering response was the construction of the object shelter, commonly known as the sarcophagus. Built in just 206 days under lethal radiation conditions, it was a desperate 400,000 cubic meter tomb of concrete and steel. To visualize that volume, imagine filling an entire professional football stadium to the brim with wet concrete. It was a heroic feat, but it was only a temporary bandage on a gaping wound. By the early 2000s, the structure was rusting and unstable, leading to one of the greatest megaprojects in human history, the new Safe Confinement. The new Safe Confinement is a marvel of modern structural engineering. It is a giant arch standing 108 meters tall, high enough to comfortably house the entire Statue of Liberty. It spans 257 meters, which is longer than 2 standard soccer pitches placed end-to-end. Weighing 36,000 tons, it is the largest movable land-based structure ever built by man. Because the radiation at the reactor was still too high for workers to stand directly over it, the arch was built in 2 halves on a nearby site and then slid into place on massive Teflon-coated rails. This $2.1 billion shield is designed to last for 100 years, giving robots the time they need to eventually dismantle the core and remove the fuel. It is a titanium-clad witness to the fact that we can spend billions to contain a mistake that took only seconds to make. Behind the scenes, the RBMK reactors that remained in operation across the Soviet Union underwent a massive re-engineering process. The fatal design flaws were finally addressed, the graphite tips on the control rods were shortened, and the rods themselves were redesigned so they would never again cause a power surge when inserted. The operational reactivity margin was strictly enforced by automated systems, and the fuel enrichment was increased from 2.0% to 2.4%. This change in chemistry makes the reactor much more stable and effectively neutralizes the positive void coefficient that led to the explosion. Engineers also installed 80 additional fixed absorber rods into the cores of all operating RBMKs, essentially adding permanent emergency brakes that can never be removed by an operator. These changes turned the RBMK from a temperamental beast into a much more predictable machine, though no new RBMKs were ever built after the disaster. The echo of Chernobyl led to the creation of WANO, the World Association of Nuclear Operators. For the first time, every nuclear plant in the world began sharing safety data and peer-reviewing each other's operations. The disaster proved that a nuclear accident anywhere is a nuclear accident everywhere. We had seen warnings before, such as the partial meltdown at 3 Mile Island in 1979 or the Windscale fire in 1957, but the lessons were often treated as isolated incidents or capitalist failures by the East. Chernobyl shattered that delusion. It showed that when engineering is compromised by political pressure or a culture of silence, the laws of physics will eventually act as the ultimate judge and jury. This disaster is a mirror of systemic decisions. It reminds us that cost-effective and safe are often in a tug-of-war, and when we cut corners on the foundation of a project, the entire structure is destined to fall. Chernobyl wasn't just a failure of pipes and fuel rods, it was a failure of the human ego. It remains a haunting reminder that we must respect the immense power we have harvested from the heart of the atom. If you found this deep dive into the mechanics of catastrophe insightful, make sure to hit that like button and subscribe for more engineering deep dives. Now I want to hear from you in the comments. In our rush toward a carbon-neutral future, do you think nuclear energy is a risk we have to take, or is the ghost of Chernobyl proof that the stakes are simply too high? Let's start a discussion below.